diffraction, interference, and the superposition. So let's begin. So the main thing that we're going to be looking at here is diffraction. All right, the first thing. So diffraction really happens when waves actually hit objects, right? So we have a wave here propagating, and then when it hits these lines, it actually creates some amount of altered waves, right? So these are diffracted waves, right? And where certain parts of the waves meet, we have something called constructive interference. And where certain parts of the waves touch, we have destructive interference, where there are no waves traveling, propagated in these areas, right? And we're gonna end up looking at this principle really and not really and truly in and of itself through the Young's double slit experiment, right? So we're looking at how waves travel around objects, right? So waves bend around edges and obstacles or gaps, right? To a degree of and a degree of spreading occurs, right? So we end up with spreading, right? Depending on the size of the gap relative to the wavelength of the wave, right? And we're gonna be looking at some stuff there. Now, the first thing that I would like to go through is actually coherence, right? So coherence is something really important as it relates to phases, right? As we discussed before, right? Here we have an intensity graph here. So remember the relationship intensity is directly proportional to the amplitude squared. Should you remember that? So in context of waves, coherence refers to the properties of waves where two or more wave sources maintain constant phase or relationship over time, right? So coherence is crucial in understanding the phenomena of interference and diffraction, right? So when two waves are coherent, right, they maintain a constant phase over time, right? So we have a wave here, right, and we're just looking at the fact that they're in a specific phase, right? If it maintains this phase, or if we have two or more waves that maintain constant phases, they are in coherence with each other, right? We have temporal coherence and we have spatial coherence, right? I won't go too far into temporal versus spatial coherence, really and truly, right? But temporal speaks to time, right? So so it really is a measure of how consistent the phase is over a period, right? While spatial coherence really measures the extent to which the wave fronts are uniform across a given space. So here we have wave fronts, right, that have temporal and spatial coherence. They're really, really simple, just lines, right? We have waves that are temporally coherent but spatially incoherent, right? So they are at the same distance apart, right? But different spaces, right, are there between them. So we end up with a wavy pattern, right? We also have, let's say, we have spatial incoherence where the wave fronts are just straight like that. But the temporal differences, there are different time differences between different areas of the wave, right? That is somewhat similar to the longitudinal wave. And then we have spatial incoherence, right? Or well, spatial and temporal incoherence. That's what I mean, right? Where we have waves mal shaped, right? And then different timings between them, right? But coherence basically speaks to the fact that if two waves are coherent, right, they maintain the same phase for a period of time, right? Same spacing, same timing, right? So that's what coherence is speaking about. Now we're going to look at the ripple tank experiment for water waves, right? And what we're trying to observe here is how waves spread out after passing through a gap. And we must compare this to wider gaps to see what is the relationship between gap size and the waves. Alright? Let us begin. So we have the waves here. Alright, so let's produce some waves. Alright, so we understand this thing. We should remember this. Alright? So this should be working fine. So let's have a look at this. So we are producing a wave here and we have a gap here. So we see that the wave actually changes its direction and its wavelength, and it starts to create this diffraction pattern as it goes through this gap, right? So we're seeing this and we're understanding this, right? But what happens now if we decrease the size of the slit, right? So we decrease the size of the slits, we're seeing a different pattern. As what happens if we increase the size of the split now? The slit, the wave shape changes, right? So we're looking at how the wave changes with the width of the slit. What happens if we have two slits, right? We have two diffraction patterns that then interfere with each other. And we're going to be looking at this concept of interference, right? So I want us to understand that. So we're just focusing on the one slit for now and looking at the fact that as we change the width of the opening, we change the form of the wave itself, right? And we're going to be looking at the science behind that, right? So diffraction really and truly gives us, right, some evidence into the wave-like nature of light. Now, light is an interesting thing to look at because light isn't a wave and light isn't a particle. Is it both? Kinda and kinda not really, right? But we're just looking at one nature of light. Light is one thing with two natures, a particulate nature and a wave-like nature, right? So we're looking at the insights into the wave-like nature of this phenomenon, right? But here are the diffraction waves on the left, right? The image, right, through as it goes, the wave rather, as it goes through a narrow slit, right, produces this interference pattern, right? But if we have a larger slit, we see that the wave broadens, right? So the wave becomes a bit broader, right? So it changes the shape of the wave, right? As opposed to if we had slits in the wave, or if we just have a huge barrier, we can see how the wave changes, right? With the different diffraction patterns being created. Yes, you must be able to produce diagrams of these diffraction patterns. It must be done, right? You must be able to produce diagrams of these diffraction patterns. They are very much important, right? Let's have a look at this. So wavelength and wave behavior. So the degree of diffraction depends on the wavelength of the wave relative to the size of the gap or the obstacle, right? So if the wavelength, right, is larger than the gap size, we're going to end up with this nice circular diffraction gradient, right? Or not gradient, but diffraction pattern. But if the wavelength is much smaller than the gap size, we're going to end up with this more squarish, this more cuboidal pattern, right? And this is only if they're under the same conditions per se, right? Same thing that we're seeing here, gap size and diffraction. Narrow gaps cause more significant diffraction. So larger diffraction they affect a larger area, right? And it's more noticeable. While if we have a wide gap, we have a smaller diffraction effect, which is less noticeable. Yes, these are things that you need to know, right? As it relates to understanding diffraction, must be known, all right? If we have a large wavelength and a large diffraction, you should come up with a if we have a large wavelength and a large slit, we should come up with our large diffraction. Small wavelength, small slit, small diffraction, right? But if we vary the size of the slit and keep the wave the same, right, we can see how varying sizes of slits may affect the wave diffraction. That's all we're looking at. All right, all we're looking at. Narrow slit, larger diffraction effect, right? Narrow slit, larger deflection effect, right? Effect rather. And if we have a wider slit now, we have a smaller diffraction effect. That is what we're trying to accomplish here. Really easy and simple. Are there any questions or concerns so far? Any issues at all? It doesn't matter what it is, it doesn't matter at all. If you have a question, ask the question. No? Alrighty. Superposition of waves now. Superposition, sorry, well, my bad. Superposition rather, right? It looks at how waves of a same, well, it's not really that they're in the same phase per se, but looking at how waves interact when they meet in the same point in time. So okay, so yeah, they're in the same phase, all right? That's what it's speaking about, right? So how waves in the same phase interact, right? In this cell, when the particles are at the same place in the same time, right? We have waves overlapping. This is what we call superimposing. They superpose, right? This is what we're speaking about. The principle of superposition states that when two or more waves overlap, the resultant wave displacement at any point is an algebraic sum of the displacements due to each individual wave at a point. So we end up with an additive nature, a linear nature, and a resulting nature of wave superposition. Right? So when waves are in the same area, when they overlap like that. In the additive nature of superposition, the resultant displacement is calculated by adding the two displacements, right? Therefore, we add the displacements and we end up with having a larger amplitude, right? With the linear waves now, superposition applies in linear waves, meaning that the waves do not alter each other's shape or energy. It doesn't. And the resulting wave now may be larger in amplitude or smaller in amplitude. So the fact that we have an additive nature, meaning that if we have two positive amplitudes, they will add. But if we have a positive and a negative amplitude, they will subtract. Right? We're going to be looking at that nature of wave superposition. And it is very important when we start to speak about interference patterns. Now, this is a sinusoidal interpretation of waves, and this is the electron. We're going to speak about the fact that the electron is not a particle, but it is a wave, right? As it relates to atomic species, right? But really and truly, before we get into all, start talking about stuff like that, right? We're just looking at the sinusoidal wave, and psi is what we call a wave function. For the persons who are interested in physics, really and truly, you would have heard of Schrödinger, right? Erwin Schrödinger and his understanding of the wave function, right? So psi is what we call a wave function. So we're looking at multiple wave functions overlapping. This is what we call the superposition of these wave functions, right? And I'm not sure if you know, but I'm getting a bit excited because I just love this. Physics is just brilliant, right? But we have a superposition of two sinusoidal waves, and we end up with psi. So we have psi 1 and psi 2 overlapping to give us psi, right? Overall. So we see that where, hold on, let me get my pen, let me show exactly what I'm talking about. The additive nature of superposition. There's a displacement here, x1. There's a displacement here, x2. They add to give this overall total displacement here, x3. And same thing here, they subtract x1, x2, subtract together to give x3. But it's really, when we really call it additive, we still call it additive. It's just additive in the negative direction, right? In the negative y direction. Alrighty? So we end up with new amplitudes when our waves superimpose. Alright, and just a hint, it has nothing to do with physics right now. But when two electron waves superimpose, they create a bond. Right? When you go to university level chemistry, then we'll discuss that at great lengths. Alright? And then we'll have to solve the equation. But it's fine, the equation is like huge. We'll not talk about that right now. Alright? But interference is what we're coming to talk about now, alright? Interference speaks to the waves, right, of different sources superimposing, right? Leading to a new wave pattern emerging, right? So it's a phenomenon where two or more waves overlap or combine, resulting in a new wave pattern. And this is due to the principle of superposition. Because if they superpose, we're going to end up with new amplitudes. If we have new amplitudes, we're going to end up with a new wave formation. That is the understanding of interference. We have constructive interference, where two waves are in phase, where their crests and their troughs align. And because we're talking about crests and troughs, these are talking about what type of waves? What type of waves are we talking about? Longitudinal or transverse? Waiting for an answer. I'll sit here and die on this hill until I get an answer. No. Transverse waves have crests and troughs rather. Lovely. Remember that longitudinal waves have compressions and rarefactions. Okay. So here we have constructive interference. When two waves that are in phase, meaning that they're their crest. For example, this is wave 1 and this is wave 2. Right? What they're going to do, we're going to have an additive nature resulting in a larger amplitude. For example, if we look at interference with sound waves, it will produce a louder sound. Alright? Destructive interference now, right? When they are out of phase, let's say that this is wave 1 and this is wave 2. It will create a line. Destructive interference. Right? It either will create a line or it will create, let's say, a reduced amplitude in either direction. It reduces the amplitude, or if it completely destructs, the wave will be completely destroyed. For example, in a noise cancelling headphone, when noise in the surroundings, right, are allowed to reach the pinna, right, we can hear it when we're talking about the physics of hearing. But noise cancelling headphones interpret the sound in the surrounding and produces a wave that is completely out of phase with the noise in the surrounding, cancelling it out, so you get noise cancellation. Waves are very interesting, right? That is how it works. We create destructive interference to get noise cancellation. All right? So here we have constructive and destructive interference, right? So in A, right, we see two waves that are in phase. When they meet up on each other, they end up in constructive interference with a new larger amplitude. When two waves are out of phase now, they create destructive interference. And you know, I'm a chemist, so I have to talk about chemistry, you know. If two electrons coming from two different atoms, right, their orbitals are wave functions. When the wave functions combine together in phase, it creates a chemical bond, constructive interference. If they don't overlap, if they're not in phase, they do not create a bond and they push each other away. Destructive interference. Right? So this can be applied in chemistry and in physics. Alright? And that type of chemistry is actually called physical chemistry. So where physics gets intertwined in the chemistry, it becomes the best thing ever. Alright, but yeah, so this is lovely. Destructive and constructive interference. Now let's speak about Young's double slit experiment. Alright? So in 1801, Thomas Young carried out an experiment in which the wave nature of light was demonstrated. A monochromatic light source is oh my gosh, hold on. I just lost English a while ago, couldn't speak English a while ago. So a monochromatic light source is incident on the first screen, right, which contains a slit. The emerging light then arrives at the second screen, which two parallel slits, slit S1 and S2, right? So we have those. These slits serve as sources of coherent light. What is wave coherence? Wave coherence speaks to the fact that the waves are in phase. Talk about that in the beginning of the PowerPoint, right? So we're looking at that. The light waves emerging from the two slits then interfere and form an interference pattern on the visual screen. The bright bands show us an interference maxima, which is constructive, and the dark bands show our interference minima, which is destructive. So here we see that the waves cancelled in these dark regions. But now we can see the actual amplitude as the waves are amplified through superposition, right, to give the white markings there. So we have maximum, minimum, maximum, minimum, maximum, minimum as it is displayed on the screen. Let's get into the maths of it. Trigonometry, the best thing about. Now, figure 14.2.2 shows the ways in which shows the ways in which the waves could combine to interfere constructively or deconstructively. All right. So the light traveling through slit 1 and slit 2, or the waves traveling through slit 1 and slit 2, right? Notice that these are supposed to be in phase, right? So when they're in phase, at P1 we'll have constructive interference. Notice that the waves are in phase. At P2, they are out of phase. This will be destructive. Are you guys following so far? All right. So at P1, we'll have a pattern. At P2, we'll have no pattern because the waves have been cancelled out. The geometry of the double slit experiment interference is there now, right? The geometry of the things. How light traveling from here and here touches at meet at an exact point, right? That's just the geometry of the slit experiment. So we cannot get two different rays, ray 1, ray 2, and an incident ray, and we have an angle theta and everything, right? And a distance y between the point of, between the midpoint, right, and that point where we have the light. Now, why is the geometry here? Why does it matter? We're not going to go through the geometry now, but we have equations that we will look at. Alright, I just want to make sure that we understand what's happening, how the Young's double slit experiment shows the wave-like nature of light. Because if light was a particle, right? If light was a particle, it would just stop here. Done. But since light is a wave and it propagates out now, we can see the fact that it will produce an actual pattern. So light is not a particle if you observe it. But we'll talk about that observance thing and those type of stuff, right? So it's the single slit diffraction minima, right? We're gonna be talking about that, right? Where we're gonna be looking at the areas of destructive interference, right? So that the minima speaks to the dark fringe, right? In the areas that are not where the maximum are. So looking at this wave, how the waves are distributed here, right? These areas y1, y2, these areas are where we have our minima, right? And we're going to be looking at what's happening, right? And this comes from the angles. So if we have a wave coming directly through where the angle is 0, sine theta would be equal to 0, right? And then as we have angles now, we look at the sine variations where sine theta is equal to lambda divided by the area of the slit and stuff like that. We're going to be looking at the derivations for both constructive patterns and destructive patterns. Alrighty? So let's have a look at the derivation. In the case of the single slit diffraction, the position of the first diffraction minimum is found from the condition sine theta is equal to lambda over A, where A is the area or the width of the slit. Remember the diagram. The diagram said at y1 sine theta is equal to lambda over A. Looking at the first one, right? So theta is also A is the width of the slit and theta is the angle at which the first minimum occurs, right? From the small angle approximation of trigonometry, right, we can say that if the angle is very, very small, then sine of said theta is approximately equal to that theta, right? Therefore, theta is approximately equal to lambda over a. Are we following the derivation? I want to make sure that we're following, so I don't want to go too fast. So through the small angle approximation, sine of that angle theta is approximately that angle theta. Now we can remove the sine from our equation. Theta is approximately equal to lambda over a. Now the position of y on the screen, right, of a diffraction pattern can be related to the angle theta using basic trigonometry. Basic. You know why? Because if I have an origin of a light here shining at an angle like this, right, and we have the slit here, right, an angle like this. If I look at this, I can also create a rectangle here, well, a triangle here rather, right? Right angle triangle, and I can use trigonometry to define the length of this side, which is the length or the width of the slit. I can use trigonometry, right, to do so. But when no one have to look at the visual renditions of this, the syllabus does not cause for it. But I do them anyways, because you will need them to understand it fully. Where we end up with y is equal to d tan, because tan is a trig function that we use to find that side of the triangle. Theta, d is a distance from the slit to the screen. Therefore, we can approximate once again. Small angle approximation, since the angle is so small. Y is approximately equal to d theta. Alright? Sub equation 2 into equation 3, and we end up with now y is approximately equal to d times lambda divided by a. We can fix it up now, thus y is equal to lambda d divided by a. Is everything there fine? Is everything there fine, guys? Right. So the math isn't that bad, because we don't go into any calculus. It's just algebra. Right? It's just algebra. And we'll use small angle approximations to take out the sine or the tan anyways. So it should be fine. Alrighty? So let me go back slightly. We're looking at that first angle there. Right? That first diffraction reading there. The second one would be 2 lambda, then 3 lambda, then 4 lambda, then 5 lambda. So if on the exam paper they ask to calculate the fourth minima, the fourth minima, right, is going to be in the ratio, right, of sine theta is equal to 4 times lambda divided by a, and you can take that to give us now y is equal to 4 times lambda times d divided by a. It's just simply the amount of time. This is the first one, therefore it's multiplied by 1. The second one, the lambda would be multiplied by 2. The third one, the lambda would be multiplied by 3, and we move on with our lives. But if we look at the negative now, if we're going to look at diffraction gratings that are negative theta, then we'll move into negative lambda. But this is the syllabus, this is the equation that the syllabus gave us. So we're just working with that. Y is equal to lambda d divided by a, where y is, what is y? Y is what? The position on the screen, right? So we can find the position of that minima. The position of that minima is the wavelength of the wave times the distance from the slit to the screen divided by the width of the slit itself. That is what it is. Describing the condition for destructive interference now, right? So I have to understand how this generally works, right? So there's an entire explanation here. We start off. So when light passes through the slit, right? So we're just looking at that. So when light passes through the slit of a width A, light emerging from different points across the slit interferes with itself, right? To observe the diffraction pattern, we must assume that the light wavefronts are passing through different parts of the slit, and they can now interfere constructively or deconstructively. So what we're saying is that we have two slits, light that travel through Yasa and light that travel through Yasa. When them touch, them interfere constructively or deconstructively. Full stop. That's what we're saying. Alright? The path difference for the two rays now. Consider two rays of light coming from 2 points on the slit that are a distance a apart. The two rays will travel different wave path lengths to a point on the screen, and this difference in the path length determines the type of interference. Remember when we said the difference in the path length? Where we have the different phases from the first thing. So we have wave 1 and we have wave 2. The difference in this path length will determine whether or not we have destructive or constructive interference. If there's no difference, if the difference in the path length is 0, we'll have constructive. If the difference is 2 pi, then we'll have destructive. Right? 2 pi radians. Right? Or if it is 180-degree difference, right, then it will be destructive. So it's destructive here, but if it is just 0, then it is constructive. All right, so we're looking at that. So 0 means that there is no path difference, meaning they're completely in phase. 2 pi radians mean that they're one entire oscillation out of phase, therefore they're opposites to each other. You'll have things like this where they're complete opposite, and this will now give you destructive interference. Hopefully you guys following, and hopefully if you guys have a question, you ask the question. It is important that you do if you don't understand something, because if you miss it, you might drop it and never get it again. But really and truly, you guys, when you go to class and stuff like that at school, then everything should be good. For the persons who don't have that luxury and that privilege at the moment, if you have a question, ask it. Alright? So, everything here should be fine. Describing the condition for destructive interference now, right, as we stated earlier, we're going to be looking at that. So at a point on a screen at an angle theta relative to the central axis, right, what we're saying, if the slit is right here, the central axis would be here, and we're looking at a point P here, right, at an angle theta, right? So the path difference between the two rays is given by the path difference, which is a sine theta, right, where a is the width of the slit and theta is the angle relative to the central axis, right? So we have that there. So the condition for destructive interference now, we must have the path difference between the two have a phase difference of around pi, right? So looking at that, the wave distance of pi, right? Half of our wavelength, right? So you can have destructive interference using pi, but you have complete destructive if you have 2 pi, right? But we can look at pi here. Thus the condition for destructive interference is the path length m lambda, where m is an integer 1, 2, 3, 4 going onwards, and lambda is the wavelength of light. Therefore, if path difference is m lambda and path difference is a sine theta, therefore we're going to have a sine theta is equal to m lambda. This is also an equation that we have in the syllabus. Alright, so looking at the points there are the condition for destructive interference, right? And remember, as I said, that is one, if that's the first diffraction reading. If it's the second or the third or the fourth or the fifth, that's why m can be an integer from 1 to infinity. It's either the first, which is 1, the second is 2, the third is 3. So if an exam question comes up and you're asked to calculate the fourth, your m is 4. Alright? So equating the path difference we have that as I just stated before, right? So this is the condition for destructive interference in a single slit diffraction pattern. So it tells us the angle at which the dark fringes or the minima occur, resulting in interpreting the result now, M1 is the first minimum, M2 is the second minimum, and so on, as I've been saying. And the central maximum is going to be theta equals 0. So we're looking at what areas on the screen do we have these dark spots, which we call minima. At what angle is the first minima? At what angle is the third minima? We must be able to define these things. We must be able to calculate these things. Alright? It is not hard, It's just a lot of complex terminology for some persons. But really and truly, A sine theta equal M lambda, that's not a difficult equation. Right? It's just to remember that A sine theta is indeed equal to M lambda. Right? But that is that. Using diffraction gratings to determine the wavelength and frequency of light as well, we can use something that we call a diffraction grating, right? So it has multiple slits in there and we end up with a diffraction pattern like this on a screen, right? So it's an optical device that disperses light into different component wavelengths, and it consists of a large number of equally spaced parallel slits. I don't remember if it was 2014's paper asked you to draw a diagram of light passing through a diffraction grating, and some persons couldn't do it. That's when I was tutoring in person though, because I do tutor sometimes in person, right? So some persons couldn't do it, so we need to remember how to do it, right? So you have light source for persons who cannot draw a light source, right? You have a diffraction grating. Let's show that it has some slits in their diffraction grating. The pattern is going to have a pattern here, a pattern here, a pattern here, right? Just showing light, and it should disperse. My bad. It should disperse at different angles out to give the different grating, right? And they're all at some angle theta to this slit where it appeared out of, right? But the grating really splits light, produce a diffraction pattern, and we have a diffraction grating equation because obviously in physics we have an equation for everything. But notice now that it is the same thing as the other equation before, where we used to define destructive interference, but this is now d sine theta is equal to m lambda and not a, where d is the distance between the adjacent slits, are also called the grating space. So the grating space times sine of the angle, right? The angle relative to the central line, right? Central axis, which is equal to m, which is any integer plus or minus 2, right? Times the wavelength of the light that we're describing. These equations are really simple. Alrighty? Understanding the grating equation now, the grating equation tells us where the maxima is. So where we spoke about where the minima is with destructive here, this now shows us the maxima. So if we always have sine theta is equal to m lambda. If we have a here, we're looking for minima. If we have d here, we're looking for maxima. That is the difference, right? So far. Let's look. So it shows us the maxima, right, which is dependent on the wavelength and the order m, and the diffraction, the grating spacing d. Measure the angle theta of the diffraction maxima. So we shine monochromatic light through the diffraction grating and measure the angles theta 1, theta 2, theta so on, right, where the bright spots or the maxima occur for different orders of m. And then we determine the grating spacing. This is the distance between the adjacent slits, right? It can be obtained from the number of lines per meter, where d is equal to inverse n. So the distance, right, or the grating spacing is 1 over the lines per meter. Using these values, we can then solve for the wavelength. Because we can rearrange, we can transpose to find lambda, where lambda is equal to d sine theta divided by m. And obviously, if it is the first maxima we're looking for, the order is going to be 1, so m will be 1, so lambda will just be d sine theta. Right? This 2 is going to be half d sine theta. 3 is going to be a third of d sine theta. Right? That's just how it works. And how you get d? If you're given the number of lines per meter, you better drop a 1 on top of it to get d. And we put it in front of the sine theta. It's not hard. We just need to remember these equations and put them down. You can make a formula sheet when you're going through. And just have all of them on your formula sheet. Separate it by your topic. So you have module 2, diffraction. Drop all the diffraction equations right there. Okay. Example of wavelength determination. So let's assume we have a diffraction grating of 5,000 lines per centimeter. So n is 5,000, right, lines per centimeter. And we are shining light of an unknown wavelength. We don't know the wavelength. And we want to determine the wavelength using the first order diffraction. M is equal to 1. What is the first thing we do? Step 1, convert the number of lines per meter, right? So we have per centimeter. We'll convert it to per meter. We times it by 100. So really and truly, it is 500,000 lines per meter. That is n. Second thing we do. Now, the diffraction, the grating spacing is what? Somebody tell me, what would the grating spacing be? 1 over what? N, right? Yes, guys? We're following? 1 over n. Lovely. Which is 2 times 10 to the negative 6 power. What is the next thing that you would do? You measure the angle. So in this case, let's say that the angle is 30 degrees. Next thing, we apply the diffraction grating equation for m equal to 1. And we end up with lambda is equal to d sine theta over 1. Where d is 2 times 10 to the negative 6. Sine, 30 is theta. And it is divided by 1. If we are good students of mathematics, we should know that sine of 30 is always a half. Right? Therefore, the answer must be a half of that, which is 1 times 10 to the negative 6 meters. Right? Or 1,000 nanometers. So, hold on. Is it 1,000 nanometers or what? Is that a typo? But yeah, so this is how, it may be a typo. No, 1 times 10 to the, this feel like a typo. Typo. But yeah, so you guys get the gist of how you're calculating these things. Wavelength determination, right? So if they describe an experiment, right, a simple diffraction experiment, and they ask what's wavelength of light, this is the procedure. Alright, you should know how to do this, alright? So we're just working through it. Calculating the frequency of light now. We know that c, the speed of light, right, which is 299,792,458 meters per second, which is roughly 3 times 10 to the 8th. So c is the speed of light, lambda is the wavelength, and f is the frequency. Rearranging the equation to get frequency, we'll have f is equal to the speed of light divided by the wavelength. Therefore, the speed of light is divided by the wavelength there to get the frequency. So they can also ask you, okay, from this diffraction equation or diffraction experiment, determine the frequency. First thing you need to do is determine the wavelength, like over here, and then use the c is equal to lambda f to now find the frequency, which is easy because c is equal to lambda f. Therefore, f is equal to c over lambda. And we move on with our lives. Then we take the speed of light and we divide it by the wavelength that we found in the previous part of the question. Alright? And we end up with the answer in hertz. Okay. The nature of light as electromagnetic radiation and the reference to its diffractive properties. We know that light is an electromagnetic wave. that oscillates both its electric field component and its magnetic field component, right? And we know that electromagnetic radiation, which is light, can travel through a vacuum at the speed of light, right? Which we stated was 299,748. And let me just leave it at 3 times 10 to the 8th, right? 3 times 10 to the 8th, right? So we have that there. So it does not need a medium to propagate. So this makes light a unique form of energy capable of traveling across empty space, right? So let's look at this, the wave-particle duality of light. Now, it was proposed by Louis de Broglie, which a picture of him is here, right, in 1924, right? And it suggests that particles like electrons exhibit both wave-like properties, right, as well as a particle-like properties. The property rather. The picture there under de Broglie is the picture of an electron. The electron is a standing wave around the nucleus. Therefore, where you don't see the bright lines here is a node, and where the bright line is an antinode. It is a standing wave around a nucleus. Right? So electrons are not particles and they're not waves. They are wave particles. They have one matter, two natures. Right? Light behaves as both a wave and a particle as well, and this is why it can go through nothing, right? Because waves have to have something, a medium to propagate through. But since light is both a particle and a wave, it can move through a vacuum, right? So looking at that, so this is why it exhibits diffraction, interference, polarization, all these different things, because it is a wave and a particle. I'm not sure how many persons are on social media and who saw the picture of the photon, right? I think they had a depiction of an actual photon, which is a package of energy, which is a high energy electron. But that's a particulate picture. It's a picture of a particle, but light is also a wave. So there's the wave-particle duality here, right? And it also lends us to our understanding of what Schrödinger was trying to say when he was speaking about, right, the outlook, right? Meaning that light and electrons behave as particles when they are not observed, right? And when they are observed, they behave like waves because we have to interact with them in order to observe them. So with the Schrodinger's cat experiment thingy, what he was saying is that if we have a cat trapped in with some, let's say, radium or some poison or something, right? Unless the cat is observed, it is both dead and alive. It is observed that the cat is both dead and alive. What we're saying is that it's either dead or alive, but we don't know. The same thing for light. If light is traveling in the vacuums of space, it is either a particle or a wave, unless we interact with the light or unless we observe the light. We don't know whether it's a particle or a wave. Therefore, it's a wave particle. That is what we're discussing here, the wave particle nature, the wave particle duality, right, of the light. But really and truly, that is where we come to a close with the electromagnetic spectrum. Your syllabus asks you to know the specific wavelengths, right, for light. You need to know the specific wavelength range for visible light. We'll start from gamma rays going straight up to around, I think, infrared. I don't think you need to go to radar, FM, or TV, right? But these are sections of microwaves. So I would ask you to know the regions of the spectrum that encompass gamma rays, X-rays, ultraviolet rays, visible light, infrared, and microwaves. You need to know the numbers. It will appear on paper ones and it can appear on paper twos. And that is it. Alright, so let's have a look at this. You can take a picture if you would like. It's fine. Right, these are the wavelength ranges that I looked for and tried to skim through. Right, the frequency ranges and the wavelength ranges and the applications of these different regions of the electromagnetic spectrum. Right, we will be looking at visible light in the next PowerPoint as we go through optics. Alrighty, that is it.